We are going to begin Chapter 6 today, Structural Analysis, and we're going to begin with a discussion of trusses. So one of the things I really enjoy about statics, about the study of statics, is that you see statics problems everywhere. Whether it's a chair and a table, or a bicycle or a car, your house, any building, or a bridge, you see statics problems in action. And that's really one of the cool things about this subject, I believe. And today we're going to talk about bridges. So here you see an example of a bridge. This is one that's close to Boise State campus. Clearly it's an arch kind of support. It's got some members here we'll call trusses. We'll talk about what those are. And here you can see it from the inside of the bridge looking down. It also has these strings, which are tension members, and you can see them over here sort of. But anyway, those are special types of members. And if you remember about strings and cables, ropes, you cannot push them. They can only be in tension, but they have some special properties, which we're going to talk about in a little while, which makes them very unique as far as construction members or members for use in construction. But anyway, I love bridges. Bridges are pretty. This one's a very architecturally pleasing bridge, I believe, in my opinion. Then we have this other one that's also next to the Boise State campus. It's not quite so pretty, in my opinion. It's kind of ugly, but it still shows a lot of examples of trusses and bridges. Trusses are made of triangular kind of members, which we're going to talk about in a moment. If you look inside your house, if it was before it was finished, this is my unfinished garage, and you can see roof trusses. And trusses again are made from triangles as we go. Even in my finished garage you can see that this support here that's holding up the garage door opener mechanism is also built like a truss. So what is a truss? Well, in Chapter 5 we talked about forces that were external forces that were applied to rigid bodies. Those external forces could be a load, but they could also be the reaction. All of those things could be the load or the reaction. Those are considered external. However, you can see from this mechanism that clearly there's more to it than just a load on a stick or a load on a beam. So what is going on the inside of a material? So that's what we're going to look at here in trusses. We're going to look at the internal forces inside structures, trusses, frames, pulley systems, and machines. Then in Chapter 7 we're going to look inside beams that are under a bending load and see what they look like on the inside. So what's a truss? Trusses are made of members and joints. A member is the member. The joint is where they're joined together. Plane trusses are two-dimensional trusses. That's kind of the second or another definition of two-dimensional is plane. And the basic element is a triangle. In other words, if you were to build this rectangle here and pin them together, you could probably see by observation that it wouldn't be very sturdy. In fact, it would probably collapse. If you put any kind of a load on it, it would collapse. Or if you put a load like here, it would become a parallelogram, which would be an unsteady kind of or unstable kind of situation. So we make them sturdy and steady by adding triangle elements, or from here to here, and then we form two triangles. Now that could be two triangles in that way, or you could do it this way, either one. And both of those work in terms of making it a rigid structure. All right, here are some assumptions for our study of trusses. We're going to assume that all members are two-force members, and they're going to follow the two-force member rules. And if you remember from Chapter 5, two-force members have a force applied at the two ends. They are always pinned at the two ends, and the line of action applies. In other words, if you pull on this end, pull this way, then the opposing force has to be along the same line of action as the original force. If they are pulling in tension from the ends, then they're also pulling in tension in the middle. In other words, the two-force member is going to be in tension no matter where you observe it, no matter how you cut it. If you were to cut a string in half and pull it from the inside, it's still going to be in tension. So one of the questions we asked, kind of a rhetorical question that we asked in Chapter 5 was, which way is the force going? And the answer is, well, it depends on your perspective. If you are on this end, you're pulling in this direction. If you're pulling on this direction, you're pulling in that direction. Now, the forces are going to be equal opposite and collinear, which is kind of what we're describing. All joints are pinned. That's the second assumption. In other words, every joint will have a pin joint, which means it's free to rotate. It cannot support any motion or any moment about any pin joint. Next thing that we're going to, and let me just mention here that even if it's riveted, nailed, or welded, it's going to be treated as a pin joint. In other words, we're going to simplify every joint to be assumed and considered as a pin joint. All right, forces will be only applied at the joints. And also members are weightless unless otherwise noted. Now, we're not going to note anything other than weightless for at least right now. So here's an example of a truss. You can see that it's made of members and joints. All of the forces are applied at the joint or at a joint. The reactions will also be at the ends, or it could be any place, I suppose, but they will also be only at a pinned connection. Well, here is the process we are going to use. It's called the method of joints, or at least this is the first process we're going to use. We're going to talk about another one or more of them later, but it's called the method of joints. And what we're going to do is we're going to find the reactions first, treat it as a rigid structure to find the external reaction, and for most purposes it's going to be a simply supported beam or a simply supported structure. If you recall from simply supported discussion, they have a pin and a roller to support them. Then we're going to find internal forces, analyze each joint to find the forces in the member. So this is kind of a key point. You go to the joint. And from there, we're going to identify zero force members and collinear members, which we're going to talk about in a moment. Start where you know something. This is also key. If you start where there are too many unknowns, then you generally can't get anywhere. And most times, by observation, you can pick a good point to start, and we're going to talk about that. Remember that you only have two equations of equilibrium, so don't start or don't try to figure out something where you have more than two unknowns at that joint. We're going to then isolate and draw a free body diagram of the joint, draw the forces in the members in the direction that you think they're going. Most of the time, that's at least in my opinion, that's the best approach. If you get a negative answer, that means you drew your arrow the wrong way. Now, in some cases, it makes sense to redraw your arrows, redo your equations, and change the signs, the SIGNs, to get everything in a positive direction. Perhaps we'll do it both ways here. There's no real right or wrong answer when it comes to that, and I think by some practice, you'll figure out what will work the best for you. Then we're going to use point equilibrium techniques. This is basically chapter 3 stuff. Break each forces up into its x and y components, solve for unknowns, and this is kind of important. Identify whether it's in compression or tension. Each member has to be identified as member or as in compression or tension. Once you've solved the joint, then you move to the next joint, and then so we'll talk and we'll show you some processes here. So what I'd like us to do then is analyze this very simple truss and try to identify the forces in each of the members. Okay, so here are two pinned joints. We have 3 members. Let's go ahead and label these as A, B, and C. I'll say this one is A, B, and C. First thing we should do is find the reactions. So I've drawn a free body diagram over here of the situation, and let's find the reactions first. All right, and we do this in the conventional chapter 5 way. I'm going to sum the moments about point A, call that equal to 0, try to find out something about that. So I have minus 500 times 2 meters plus by times 2 meters is equal to 0. So here I have by is equal to 500 newtons, and that is positive in the direction that I've drawn my arrow. What else can I find out? Let's sum the forces in the x and some of the forces in the y and see if I can find out what else is going on. So let's label this. I'm going to say this is by, this is going to be ay, and ax. So let's sum the forces in the x. Sum of the forces in the x is equal to 0. So here I have plus 500 minus ax is equal to 0. So ax is equal to 500 newtons. And again, positive in the direction I drew my arrow. And I'm going to move over here and sum of the forces in the y is equal to 0. So here I have by minus AY is equal to 0, so AY is equal to 500. Also positive in the direction that I've drawn my arrow. Alright, so that's a good way to get started. Find those reactions. Now, let's move to a joint. What we're going to do is isolate the joint. Draw a separate free body diagram of the joint. That's what I've done here for joint number B, or joint B. Now let's go ahead and solve this and see what we can find. Again, once we draw a free body diagram of the joint, generally a moment equation doesn't apply, or there wouldn't be any lever arms associated with this, so you can't really do any moment equations. The only equations we're going to do for each joint is some of the forces in the X and the Y. Alright, so let's look at joint B here. Alright, what have I got? Well, it's pretty easy to sum the forces in the Y is equal to 0. Now I know the BY is positive. I've already solved for that. It's 500. If I sum the forces in the BY, now I've drawn BC as pointing down. What does that mean? Is that I have drew it as a compression member. I've drawn it when you have a tension member, the force is pulling away from the joint. If you draw it as a compression member, it is pushing toward the joint. So let's see if it's true. I say BY minus BC is equal to 0, and I can see that BC is equal to 500 newtons, positive in the direction that I drew my arrow, so I'm going to label that as a 500 newtons positive as a compression joint. Alright, how about in the X direction? Let's sum of the forces in the X is equal to 0, and I haven't drawn a direction on BA yet, so I'm just going to do it here. I'm going to draw it as a compression joint, or a compression member. However, there aren't any other forces in the X direction, so it's pretty obvious that BA is equal to 0. In other words, there is no force in the member BA. Alright, let's move over to joint A. Joint A is over here, so I'm going to draw a free body diagram of joint A, and you can see I've got there. We've already solved that AB is equal to 0. We know that AY is equal to 500. We know that AX is equal to 500 because we've already solved for those things. Now I've got AC. If I go back up to my picture, I got AC going up there. I don't have a known direction here, but I'm going to assume that it is going to be in tension. If it's in tension, then it pulls away from the joint. And at every joint where it comes out off at an angle, it has components. I've got ACY and ACX here, but let's go back and look at the angle. This is a 2 meters by 2 meters kind of arrangement, so that's got to be a 45-degree angle. So I can label then the components as this will be AC sine 45, and ACX is equal to AC cos 45. Alright, once I do that, all we again do is sum of the forces in the X and Y. So I will say, let's do sum of the forces in the Y is equal to 0. So here I got minus 500 from that AY plus AC sine 45 equals 0. Solving that for AC is 707 newtons. Now, I drew it as a tension member. As I draw it pulling away from the joint, this component is also pulling away from the joint. Both components are pulling away from the joint, which is the only way that makes sense. When I do that, I see that it is a tension member, and I see that it is positive in the direction I drew my arrow. Now I can also double check my work if you wish, or if you want to call it that. I've solved for all of the joints. I've solved for all of the members, but I can double check this by doing sum of the forces in the X is equal to 0, and just to see if I did it right. In the X direction, I have minus AX plus AC cos 45 is equal to 0. I've already solved for AX is equal to 500. Dividing that by cos 45, I can see that AC is equal to 707. So again, I get, and it's also positive in the direction I drew my arrow, so it is a tension member. So it doesn't really matter how you get there. It's a bit redundant. You don't have to do both of those things once you find the force in the member, but you can do it either way when you solve them.